Good evening, everyone. My name is Anshuman Sen Sharma. Today's video conference is a new one, definitely. So there would be some difficulties sometimes in communication, possibly. But let us see how far we can make it successful. Now, before I start talking about the subject matter, that is flow accelerated corrosion in piping, let me first discuss certain rules which I think would be required to be followed in order to conduct this program properly. The first thing is that just type OK individually in the chat box, which you can see here. This is the chat box. If you can hear me and see the presentation. Now, second thing is that I will keep your audio feeding off mode, as I already told you. It creates noise disturbance, so please don't switch it on. If you have any questions during the presentation, yes, Mr. Shiva, I got that. If you have any questions during the presentation, please click on the raise hand option. The raise hand option, as you can see, it's there in your screen. So please use the raise hand option. I will come back to you. And if your internet speed is not adequate, please keep your video speed off. Otherwise, it will create disturbance in the system. Right. Having said that, let me get back to the subject matter. So, flow accelerated corrosion, it is also sometimes termed as erosion corrosion. It was not a very well-known damage mechanism till very recently. In fact, the whole focus on this particular damage mechanism has come after a particular incident, which you can see in this in the newspaper cutting. It happened basically in 1986, December 1986. The place was Surry County. It's a nuclear power plant in Surry County, US, in the state of Virginia. And the place or the location where it has happened is basically a pipe bend, 90-degree bend, in a feed water suction line. It was an 18-inch feed line bend. So naturally, the result of the accident was pretty dangerous. It failed somewhere here, as you can see. Now, 4 persons were working nearby. They were actually removing insulation. They died. Actually, 3 of them died right there, and 1 person died afterwards. And 2 persons were injured. And this particular incident was termed as the worst nuclear accident in US till date at that time, in 1986. And as you can see that it is, though it has happened in a nuclear power plant, where the norms and the requirements and everything are very stringent, but it happened in a feed line. Now, in a feed line is there in every power plant border, right? If you see that what has happened, because of the magnitude of the accident, now EPRI, that is the Electrical Power and Research Institute. 1 second. Mr. Par, you are not able to hear my voice? I cannot help you right now. So what happened is EPRI has started looking into the matter, and they started investigating the cause of the accident. Now the location, when they have taken a closer look, this portion was actually affected. It blew out like this. The material thickness was, nominal thickness was 12.7 mm. And the thickness was reduced to almost 1.5 mm near the rupture zone. Now this was a serious issue, and naturally a lot of investigation has taken place by EPRI, and then it was found that the cause of this failure, and it was termed as flow accelerated or flow assisted corrosion, and the wall thinning has taken place because of that. Now, if I talk about the feed line, afterwards it was found that in many other nuclear plants, for example, there was a failure in a high pressure extraction line at Fort Callahan, that was also a nuclear power plant. Then a reheated drain line reactor in the Millstone Unit 2, that is also a nuclear power plant. And not only the feed lines and the drain lines, it was also seen in the feed water heater shell in a Point Beach Unit 1 nuclear power plant. So it was happening in a lot of places, and the causes, all of those causes were attributed to flow accelerated corrosion afterwards. Now, this thing is not only happening in nuclear power plants, any fossil power plant, and particularly in HRSG afterwards, people have found that the accidents are occurring with a quite regularity, and then from all those field measurements and field information, certain ideas were formed, and people started to look into it, that what is causing this problem. Okay, so if I want to take a look at the damage mechanism of flow accelerated corrosion, first of all, what EPRI say, the definition of this particular damage mechanism, flow accelerated corrosion. So it was understood as a process where the protective oxides, which is, usually there with the carbon steel piping of magnetite layer, the protective oxide layer on carbon and low alloy steel, where the chromium percentage is very low, they are getting dissolved into a stream of flowing water, or sometimes a water and stream mixture. That means it is happening in a single phase flow, and sometimes in a two-phase flow of water and steam too. And this is happening because the magnetite layer, or the protective layer, is getting chemically dissolved, which is also mechanically assisted in some way. Now, when this is happening, it is termed as a corrosion. It is not an erosion. Of course, corrosion is sometimes is termed as, but it is primarily corrosion. So let us first take a look at what corrosion is, or rather, what is corrosion when we talk about the dissolved oxygen coming into contact with ferrous metal. Now, oxidation of iron, if you understand, basically three processes are there. One is the formation of FeOH2, which is also commonly called rust. Then Fe2O3, which is hematite, and Fe3O4, which is magnetite. Now, kindly keep audio off, please. Now, if I want to understand what corrosion is nothing but metal loss. Now, if I take a look inside the pipe, imagine either of these three formation of oxides is happening on the tube shell, the tube metal thickness. So suppose this is one formation of oxide, and this is another formation of oxide. Now, which one would I call a corrosion? This corrosion is the loss of metal. Now, if this or this formation of oxide gets dissolved in water and flows out, that will result into the loss of metal or thickness. In that case, I would say it is corrosion. But suppose this oxide layer is, and it is where it is formed, then I would not rather say it's corrosion, but it is actually a shale, right? And this is nothing but how the magnetite should behave. The magnetite is supposed to the surface of the metal forming a cake. Now, if I consider the conductivity of magnetite, it is definitely lower than the metal, the base metal, but it is not very low. You can say it is almost 1/48th time of the conductivity of the metal. Now, if I can assume that I am having this thing in a limited thickness, okay, coming back to this, now, if I can assume a thickness of, let us say, around less than 30 microns per square meter area, that is called the density thickness, rather than restricting the heat transfer, it is going to behave as a protective layer on the metal surface. And that is primarily the job of magnetite, which protects the metal from the interaction of the water. Now, these are all basically galvanic or magnetite. Now, if we can protect the metal from the galvanic reaction by putting up a scale of magnetite, then the metal becomes safer. So that is why the magnetite is basically termed as a protective layer. But suppose this magnetite gets and goes out, then what happens? Then instead of actually protecting the metal, this is creating a metal loss. Therefore, this is going to be a form of corrosion. Now, that is exactly what happens in case of FAC, that is flow accelerated corrosion. Now, in case heat in the water and there is no oxygen, there is a continuous formation of FeOH2 in this reaction. Now, this FeOH2 goes through a secondary reaction afterwards, and it is called commonly a Shipor reaction, and it gets converted into magnetite. This magnetite is supposed to be stable and stick to the surface, but if the pH is not high, pH is not very high, then it creates a problem. Then it starts getting dissolved in the water. pH, if the O2 is not high, if the pH is not high, and if there is the presence of reducing agent like hydrazine or something, then also it tends to get dissolved into the water. Now that will ultimately result into corrosion. Now it has been seen that this is assisted by this turbulent flow in the water, and this mechanism becomes faster. So that is where people have associated this sort of corrosion with the mechanical disturbance in the water. Naturally, this sort of turbulence will occur, in the downstream or upstream of the elbows or the valves or the reducers and such heating. So it was confirmed afterwards from the film, basically information that yes, most of the FACs are occurring nearby the elbow joints and valves and the control valves and the header joints and such, where there is a chance of increasing turbulence in the water. Now, it was resulting into metal loss, and afterwards you can see the presence of some scallop-like structure. The orange pill of like structure is resulting into thinning of the material. So this indicates that there is a dissolution of continuous dissolution of magnetite and the base metal in the water, which is resulting into this kind of appearance, right? If I want to take a look at the typical features of the FAC, then typical features of the FSC will be associated with the localized staining. Localized in the sense it will not be throughout the pipeline. It will be localized nearby the elbow joints or on the elbow joints or such places. It is resulting because of dissolution of protective oxides in this metal. It can occur in single or two-phase water. And it was mostly seen, now this is very important. This is very important. It is mostly seen in the carbon steel metallurgy used in the feed water system of the fossil power plant. In the HRSGs, it was again seen in the HRSGs that in the LP evaporator and economizer area, it is quite susceptible. So most of the HRSGs are actually suffering from this particular form of damage mechanism. And it is quite often seen, it is occurring adjacent to the bends, T-joints, reducers and valves where there is a chance of increased turbulence in the water. Okay. It's around, if I want to see the locations where it is happening, then feed water heater drains, it is both single phase and two phase type of failure are most prevalent. In fact, feed water heater normal drains are the most prevalent area where FSE is operated. Then piping around the boiler feed pump, you have seen the first case in the Surrey nuclear power plant. It is the feed water suction line. Now piping around the boiler feed pump, it's occurring. It is also occurring in the temperature supply piping and the downstream of the spray control valve. In downstream of the spray control valve, you see both single and two-phase type of FSE problem. Piping to the economizer inlet headers, especially near valves and supply teeth. Then economizer inlet header tubes. These are all single-phase FSEs. It most frequently are there where it is near to the header supply. In high pressure feed water heater tubes and tube sheets, you have seen one case where the heater shell was damaged because of FSC made of carbon steel. In the low pressure feed water heater shells, especially near gasoline drain entries, then deaerated shells sometimes, particularly in the near the fluid entry point. In HRSG, it is quite often seen in the LP section of the economizers and the preheaters and the evaporators. You know, the vertical LP evaporators used on horizontal shells, these are very, very commonly affected by FSC. Then LP evaporator inlet headers, you know, in HRSG, the tubes are all very tightly packed, which ultimately results into very short bends between two tubes, right? These are the areas where we get more possibility of FSC occurring. And of course, in a air-cooled condenser, in the inlet duct and the distribution headers and the tube are nowadays it is found, and there's quite a lot of research going on by EPRI that most of the ACCs, that is air-cooled condensers, are getting affected by flow accelerated corrosion. In this case, it is primarily the two-phase corrosion. This is water and steam combined. Now, after the study, it was found that certain areas, the flow accelerated corrosion is more severe. So based on that, it is now understood that it is basically a mass transfer problem. That is, iron transfer is taking place. As I told you, it is getting dissolved in water and then flowing out of the system. And it is depending on the factors which would suggest that the FSC will be more or less. The seal composition is one very important factor. The temperature, the velocity, and the turbulence in the local area where FAC is occurring. Since it's a chemical process, it's a corrosion process, the water pH is one more very, very important aspect. And of course, the concentration of both oxygen as well as the oxygen scavenger like hydrazine, which is very commonly used. Now, if you take a look at those factors which is affecting the FSC, we'll go in detail of it, that how it is affecting temperature, pH, O2 concentration, mass flow rate, geometry, quality of fluid, and alloys of construction. Now, if you want to actually avoid FSC problem, then these are the factors where you should put more concentration, because these are the factors which is going to tell you where to look for the FSC problem, or where FSC problem is more likely to occur, right? Let us individually see how it is getting affected. For example, effect of temperature. The effect of temperature on the material wear rate is given in this particular graph. As you can see, that this y-axis is the specific metal wear rate in terms of microgram per centimeter square per hour. This x-axis is the temperature, of course, in Fahrenheit. So, this is the location where FSC is maximum, right? Now, if I come here, this will be in terms of degree centigrade, somewhere in the range of around 150 degrees. So, FSC is not a high temperature problem, right? It is low, at low temperature, in between somewhere. So, you can say around 120 degree to around 240 degrees is the area where FSC is most likely to happen. Maximum will be at 150 degrees. Right? So this is where we should focus. This is the location where FSC is happening. Right? So from between here to here is the maximum problem of FSC can occur. Okay. Now, if I want to see the metallurgy, you see for different metallurgy, there are different degree of FSC wear rate. And it is maximum with carbon steel. As you can see, the alloy steels are coming where the chromium percentage is given. Suppose 1% is chromium or 2/4%. That is, we are talking about a T11, T22, P11, T22 material which is commonly used in the power plant. Here, FAC problems are almost negligibly small. So, the chromium contained more than 1% is understood that it reduces the FAC problem almost to nil. So that gives us one defense. Okay, if we are having frequent FAC problem, we can think about change the material. Because temperature is not something which we control. Temperature is the system requirement, right? Whatever the temperature is at particular location, that we cannot change. Yes, we can think of changing the metallurgy perhaps. Effect of pH. This is very important because primarily the FSC is controlled by the feed water chemistry, right? You don't just change the metallurgy from carbon to P11 or P22 just like that because it's very costly, right? So primarily the FSC is controlled by changing the feed water chemistry, and it is seen that pH has a significant effect. If you see here, when the pH is in the range of around 9 or more than 9, the FSC rate is coming down quite significantly. In fact, for carbon steel, almost 40 times reduction in FSC rate will occur when the pH is increasing from 8.6 to 9.4. In the range of around 9.2 to 9.4, the FSC is almost minimum, right? So that is the pH we are talking about. That would be the target pH for the feed water chemistry where we are having the FSC related problems. Then the dissolved oxygen. Now this is the most peculiar aspect of it. Usually it's commonly understood that oxygen corrosion is directly proportional to the dissolved oxygen content in water. The more the oxygen, the more is the corrosion, right? But in flow accelerated corrosion, if you take a look at this curve, then the rate of corrosion is decreasing significantly as the oxygen content increases, right? Actually, if the oxygen content is more than 30 ppb, the rate of FAC is almost minimum. You see, here the rate of FAC is almost minimum. So that is one interesting finding in terms of flow accelerated corrosion, which is totally different than other form of corrosion, oxygen corrosion. In flow accelerated corrosion, oxygen actually helps to restrict the corrosion, right? So this again gives us an idea about changing the feed water chemistry in some way. I'm going to show you how. The effect of velocity. Now again, this is somewhere we do not have much control. But yes, this is going to give us an indication or idea where we can expect more chances of FAC to occur, right? As you can see, when the increase in velocity, the rate of wear rate in the y-axis is continuously increasing, and it is increasing more with carbon steel. So this is again one more thing. Carbon steel is having much more wear rate as compared to 2/4 chrome moly, that is the T22 molecule. Or for example, T11 metal, which is 1/4 chrome and half moly. So this is one more fact, and the other factor is the location. If you take a look at the field, informations or data which were collected by ECRI, they have found that in case of FAC affected bend, it is affecting both on the outside, right after the elbow, or on the elbow itself, on the side of the elbow. No? Okay. Either here on the outside, or right after the elbow, or on the side of the elbow. Now, basically the Reynolds number changes in this location. The Reynolds number is very high in this area, low in this area, medium here, right? Now all these locations are getting affected by flow accelerated corrosion. So it is irrespective of the Reynolds number. So one way to say it is the turbulence which is affecting the flow accelerated corrosion. So when the turbulence is increasing, it is helping the protective layer to get dissolved in water and gone away, right? So now let's talk about the precaution. In case of an all-ferrous metallurgy, the only precaution that can be taken in terms of flow accelerated corrosion is changing the cycle chemistry. The feed water chemistry has to be changed into AVTO. Now what is AVTO? I'm going to tell you. It's basically all volatile treatment oxygenated. That is AVTO. Usually the most common treatment which we have in our power system or in the feed water cycle, feed and steam cycle, is the hydrazine and TSC dosing. That is the chemicals which we are using, right? AVTO is different. In AVTO, basically what we need to do is we need to increase the pH of the system by using ammonia, right? And there should not be any kind of oxygen scavenger that will be used. That is AVTO. Okay, let us take a look what ammonia, increasing pH by ammonia does to the wear rate, right? At different temperatures, as we have already seen, at around 150 degrees centigrade, the rate of corrosion is maximum, right? But now if we take a look, in case of a 0.165 1 ppm and in case of 2 ppm, the difference is coming to almost 0, right? So if we can increase the pH in the range of around 9.3, 9.2 to 9.4 or 9.6 by ammonia, we can reduce the FAC to a large extent. Now that is the only difference with us so far as flow accelerated corrosion is concerned. Change the cycle chemistry with ammonia dosing, increase the pH in the range of around 9.2, 9.6, system pH, that includes the feed water pH. Usually the feed water pH in most commonly are in the range of around 8.6, 8.8, 8.9, right? If you are having problems with FAC, you have to go for an increase of that feed water pH to around 9.2 plus. That is the only solution to FAC. Let me tell you what is AVTO, or volatile treatment oxidizing treatment. Is basically you are not using any reducing agent. That is, the hydrazine dosing is not permitted. That is one thing. You are if you are using AVTO, then the achievable iron level, that is, the iron transport can be reduced to around 1 ppb or less, even less than that. Right? That is the possible achievement by AVTO. In this case, instead of the magnetite layer, what you are having is basically a protective layer of ferric oxide hydrate, that is APOOH. Right? This is much more stable than the magnetite. And this is only possible if you are using the AVTO instead of AVTR. Because in AVTR also you are getting magnetite as a protective layer. And the other thing is that it can be used for only all-ferrous metallurgy. That means if you are having a combined metallurgy or dual metallurgy, you cannot use AVTO. That means if you are having copper in your system, for example, your condenser is having copper metallurgy, or your LP heater is having copper metallurgy, that means it brass, for example, you cannot use AVTO. This is only can be used for an all-ferrous metal. There are certain requirements if you want to change your feed water chemistry into AVTO. First of all, as you see, the elevated pH of 9.2 to 9.6 in the feed and steam cycle, right? One important thing is the cationic conductivity has to be less than 0.2 microsiemens per centimeter. Now, this is only possible if you are using a condensate polishing unit in your system. Unfortunately, less than 500 megawatt unit, there are very few places in India where condensate polishing units are being used. Unless you are getting or you can achieve a cationic conductivity of the feed at less than 0.2 microsiemens, and those who know about their water chemistry, they know that this is very, very difficult to achieve. So you must have a condensate polishing unit in your system, and of course, then another thing is that you cannot allow any oxygen in leakage of more than 10 ppb in the sea pump discharge. Right? In the condensate pump discharge, the oxygen leakage has to be restricted to less than 10 ppb. And of course, you are not using any N2H4. I don't know whether I can write it. Yeah. Right? No N2H4. There is another treatment. It's called oxygenated treatment, and nowadays, even for subcritical system, it's being used quite often at many places. In South Africa, I have seen that many units they are using oxygenated treatment. In oxygenated treatment, again, what we are doing is we are dosing with ammonia as well as oxygen at some specific locations. Right? Yeah, this is basically the upper part is the AVTR, that is reducing AVT system. This part is the OT system, that is the oxygenated treatment system. Here in the CP discharge, oxygen is dosed, pure oxygen is dosed, and the oxygen level is maintained in the range of 30 ppb above, 30 to 50 ppb in case of a drum unit, and 30 to 150 ppb in case of a one-story unit. Right? And there is another location where oxygen can be dosed. Sometimes it is dosed to maintain the oxygen level around 120 to 150 ppb. So in AVTO, the oxygen level is maintained in around 120 to 150 ppb, and there is no other chemical than ammonia and oxygen. But again, for AVTO, OT treatment, the requirement is pretty stringent. Requirement is for OT treatment again, if I tell you this, that the conductivity, the feed water conductivity has to be less than 0.15 microsiemens per centimeter. Right? So that is a pretty stringent requirement. If you can manage that, then only you can go into the oxygenated treatment. Okay. Now the precautions, if I continue with the precautions, turbulence should be minimized by proper design. Now this is something which cannot be done afterwards. So it is during the design consideration only it has to be taken into consideration that you have to reduce the turbulence. You have to reduce the turbulence here. Then for new replacement, that is if the system chemistry cannot be managed, then you can possibly think of changing the metallurgy itself, because as you have seen, that carbon steel is the metal which is mostly affected by flow accident corrosion. The same is not true for P11 or P22. Here we are having 1 quarter chrome. Here we are having 2 quarter chrome. If we use 2 quarter chrome, the chance of SSC is almost zero. You don't have to worry about FSC. Okay? And of course, the precautions which we need to take is basically, we have to have a proper inspection, sequence or system where with a proper regularity, and that means we are coming also between two shutdowns or between regular shutdowns, you have to go for a very, very thorough thickness measurement of those areas where FAC is susceptible. Now, where FAC is susceptible, I think now you can understand those areas. That means it is carbon steel metallurgy. It is in the low temperature area between 140 to 240 degrees centigrade. And there are chances of some turbulence because of the bends, and bends are primarily short bends and such. So these are the areas where we can expect the FAC. So therefore, we must have a proper system of thickness measurement in those locations. You can also check the FAC problem by monitoring the iron concentration in the steam cycle. That means the iron transport level, right? If the iron transport level increases, then that is going to indicate that yes, in your system somewhere, the FAC is taking place, right? Then you go for a proper thickness measurement. Now, suppose you find in your thickness measurement that yes, FAC is taking place. Now there are some guidelines by EPRI that what should be your step. What step you are going to take? Whether you want to replace it or you want to keep a close monitoring thereby, or you can think of maybe reducing the frequency of thickness measurement there and such. Usually the UT is ultrasonic test is done for a pipe size of more than 50 MB size. Less than 50 MB size, you can go for a radiographic test. Even for thickness measurement, it is done. In fact, I'm going to give you a link from where you can download the documents from EPRI website, where they have given you proper guidelines for both inspection as well as FAC program. Now, this is called FAC program, where you should inspect, how you should inspect, and what you should do after you get the inspection program, right? So this is the integrity of the thickness measurement. You can refer the EPRI report NT 5911. It is based on that actually. What I am going to show you is based on that. If the smallest measure wall thickness, if you are measuring the wall thickness, the smallest measure wall thickness, that is T measured, is greater than 0.875 T nominal. Suppose you have got a nominal thickness of that pipe. If the reduced thickness is greater than 0.875 Tn, then further evaluation is not needed there. You don't need to evaluate there. You can go for the normal thickness measurement. After the next shutdown, you can always check the measurement and see what is happening there, right? Nothing extraordinary steps are required to be taken here. But if the thickness is intermediate, that is between 0.875 Tn to 0.2 Tn, right? That means here we need to do some or take some more evaluation, right? If it is less than 0.2, suppose it is less than 0.2, then you don't think about doing anything. You better replace that pipe. It is always advised to replace that pipe if it is less than 0.2 T, right? If it is between 0.875 T and 0.2 T, then you have to go for further evaluation where you have to predict, based on the wear rate, based on your experience of that location, right? You have to predict the thickness which is going to be there during the next evaluation. So whatever your frequency of thickness measurement, you have to now predict the thickness that, okay, by the next thickness measurement, our thickness is going to be like this, right? And you have to take the minimum wall thickness into consideration to check whether you go for further detailed evaluation or wait for the next regular inspection. So in that case, is the T minimum, which is with which you are going to compare, is basically a design parameter. You can calculate it from the guidelines given as in the ASME 31.1. It is nothing but the thickness which we get for a cylindrical pipe with the circumferential stress into consideration. That is PD by 2T, right? So as per ASME code section 3 NC 3324 case, the T minimum can be taken as PDO by 2S plus 0.4 P. Now, this is the pressure under which it is working. This is the OD of the pipe, and this is the allowable stress of the material of the pipe, and this is the pressure again, right? So what you need to do is you need to check the T minimum from this particular. Hello. Somebody's sound is coming. Can you sound, please? Get closer. Okay. Now, you calculate the T minimum by this formula. You take the pressure and the allowable stress in megapascal. You take the DO is in millimeter. You get the T minimum in millimeters. That way, right? And then you check whether your predicted thickness is more than 90% of the T minimum. If the predicted thickness is more than 90% of the T minimum, then you do not need to, further evaluate there immediately. You can wait for the next shutdown and next thickness measurement. But if the predicted thickness is less than or equal to 0.9 T minimum, then again further evaluation is needed, right? Then this CP has to be compared with another thing that is called minimum acceptable thickness, TA. The calculation of TA can be done by following the ASME code case N5972. If your predicted thickness is more than T acceptable, calculated from this section, then this location should be monitored in the next outage. But if the local thinning is less than C acceptable, then you have to either go for repair or replacement of the section, right? So that is basically what the guideline says in terms of evaluation of FSC training and acceptance criteria, right? So what I'm going to give you is I'm going to give you this two document reference. You can write it down. One is the recommendation for effective flow accelerated corrosion program. Another is the inspection technologies. Both are the EPRI guidelines, and you can download these documents from epri.com. These are all free documents available in the EPRI website. So you can always, search for this in the EPRI website and download it, right? So that is going to be the only guideline you can follow, because they are the institution which are working on this particular failure mechanism, and most of the guidelines, those are being followed even by the nuclear power plants, are given by them, right? So that is all about flow accelerated corrosion as of now. Now, if you have any questions, then I'll be glad to answer those. You can write your questions here. Whether change of MOC? Yes, definitely. Change of MOC, as I told you, if possible, if you can change the MOC from carbon steel to something like P11, it's going to help you a lot. If you're going to change it to P22, you can almost, forget about FSC. So yes, it definitely would help the thing. Mr. Vijay Ingole, how long we can keep boiler in weight preservation? Depends on how you are preserving your boiler. If you are following the proper weight preservation methodology, then you can keep it for any number of days and weeks altogether. Okay, Kiran, I'm reverting back to the previous slide. This one? Okay. Is EPRI.com. You have to search for this document. You go for this document, recommendation for an effective flow accelerated corrosion program in the EPRI website, and it can be downloaded from there. Any more questions? Mr. Chakravarti says that, do you mean we should discard deaerator or N2H4 to avoid FAC? No. Deaerator, no. N2H4, yes. In case of all ferrous metallurgy, AVTO, if you are reverting to AVTO, then you cannot use N2H4. We cannot use N2H4. Right? So, as I told you, if you want to know more about AVTO, then we can discuss that afterwards on some other occasions. But yes, in AVTO, oxidizing all volatile treatment or oxygenated treatment, the role of NTA, in fact, N2H4 actually increases the FSE to some extent. Ms. Divakar says we are changing from AVTO to OT in some unit, then what we should be monitoring? You should monitor the oxygen, iron transport there. You monitor the iron transport there and monitor the thickness where you feel that yes, there are chances of FSE. But if you are changing into OT, I think definitely the chances of FSE is going to be minimized to a large extent. You will be having much less problem with FSE. Mr. Ingole, you were saying what are the parameters you have to monitor during preservation? First of all, let me tell you this way. This particular forum is not proper for discussing this. You have our email address. You can ask me this question in the email. I am going to answer it there. Right? Okay. And anything else? What is the limit of O2 for AVTO in low temperature area of reduced FSC. Kiran, in AVTO, basically the O2 limit is around 10 ppb, right? Well, suppose in other treatment we are going for less than 5 ppb, but in AVTO it is less than 10 ppb. So you must have a deaerator. There is no question about not having a deaerator. What you have to ensure is you have to ensure the air in leakage in the CPT area. That you have to ensure. Could I answer my question? Okay. If you have any further queries, you can always send me a mail. Perhaps in the future I can think of conducting one more such program on the subject of your interest, right? So till then, thank you very much to everyone and good night.